In this lab, you're given about a meter of wire and you need to make a coil for a motor. I wrapped it around a small battery to give it a perfectly circular loop that I could easily balance when it was hooked up to the motor. Balance turns out to be important because the force acting on this is not particularly strong, and we need it to be able to turn easily. When I had made my loop, I then wrapped the ends of the wire around the loop to keep it from unwinding. At first, when I wrapped both ends around the wire, I found that I had the wires not on opposite sides of the coil, and that meant it was going to be hard for it to spin because it wasn't symmetric. So I ended up unwinding it a little bit and putting the ends exactly 180 degrees from each other. If you look here, you can see they sort of are making a V shape, but I need them to be on opposite sides. So if you look here, you can see that the wires are now on opposite sides, and it looks like it should spin pretty well. Of course, before we actually do anything, we take it and we put it on the battery holder and we check, and it looks like it spins pretty well. So it should work when we put a battery and a magnet near it. Now, in order for it to work, it has to conduct electricity. The red paint that's on the wire makes it so that it can't conduct. I stripped off the paint on one side of the wire so that when it touched the electrical contacts, it would conduct electricity. I stripped the same side on the opposite lead. And if you look, when we put it on the battery holder, right, see it's shiny on one side and it's red on the other, meaning it will only conduct when that shiny side is down and touching the electrical contacts of the battery holder. I straighten it out so that it'll spin a little better. And we check to see if everything's all right by putting it on the battery holder. And it seems to spin okay. Now, we don't have current unless we put a battery in the battery holder, and you can see it has two contacts that conduct the electricity from the battery up through these brass leads up to our coil. When our coil is sitting there with the shiny side down, it will conduct electricity, and I'll have a small magnetic field inside my coil. If I put a permanent magnet there, it can react with the magnetic field of the coil, and you can see it starts spinning almost immediately. It's wiggling back and forth now, but it has enough force that it periodically spins. Right? That tells me that the coil is close to being balanced, but not quite balanced enough for the magnetic field to have a consistent effect on it. If I put a second magnet there, the force is a little stronger, but even so, it sort of rocks back and forth. Again, it seems to work, but not consistently. So it probably means I need to balance the wire a little bit. So if I take the wire off, I can play with it a little bit, and at some point I will get frustrated with this and try just that. So let's take that off, and we'll adjust where the wires are just a little bit, sliding one wire up so that it's a little bit more symmetric. If I put it back on, can see, and I give it a small start. You can see it wiggling already. I give it a start, now it spins quite quickly. So again, you see that the magnet is pushing on the coil when the electricity runs through the coil. Now, why do we only strip one side of the wire? Well, when we strip one side of the wire, the magnet pushes on the coil when that side is down. But because when it flips, the current is going in the opposite direction, because it's going around a circle. When you flip a circle, that turns the current in the opposite direction. If a current were going through it at that point, it would stop and flip backwards, and your coil would simply rock back and forth. We want the coil to turn, so what we do is we only strip one side of the wire, and that way it pushes when the wire is conducting, and then when it flips, it stops conducting, and the momentum of the turn just keeps on spinning from just the momentum, and it pushes again when the conducting side is down. But you can see this is spinning quite rapidly, and you can see the shiny side alternating with the red side as it spins. Now in the second part of the lab, we have a propeller hooked to another hobby motor, and that's hooked up to an LED. So we have three parts here. We have the propeller, the motor, and the LED. If we blow on the propeller, it should turn, which will turn the motor, right? Instead of attaching a battery to it, we're going to force the propeller to turn. We're going to exert a force on it. When we do, you can see the LED lights up brightly. So when we turn the hobby motor, it acts like a generator, and the LED lights up. Then we can try the same principle with two motors. I have one motor that I will hook up to the batteries, one motor that I will hook up to a light bulb, and in between is a plastic connector. So first we hook up the second motor to the light bulb, then we hook up the first motor to the batteries. What you can see is that the motor starts turning, and if you look carefully, you'll see that the light bulb lights up. That tells you that the first motor, while turning, forces the second motor to turn, and the second motor acts as a generator. So when you apply current to a motor, it turns and acts like a motor. When you apply a force to a motor, it acts like a generator and produces current. Now, if we use a 9-volt battery instead of the 3 volts from our circuit board, you can see that the light bulb lights up significantly more brightly. But that's because that the motor is turning much faster, so it generates a lot more electricity.